Okay, hello everyone. I'm Dr. Justin Essery, professor at Rice University, and I'm pleased to present today's IMC talk. Welcome to the International Methods Colloquium. The IMC is a periodic online interactive seminar discussion on the application of quantitative statistical methodology to the social sciences, sponsored by Rice University and the National Science Foundation. I'm really pleased to welcome this week's speakers, Susie Linn from Penn State University. She'll be presenting a talk entitled Treating Time with All Due Seriousness. Suzanna's talk is going to last about 30 to 40 minutes, and then she'll be available to take questions from the audience. You can call in to ask a question on the air, or let's show our toll-free line here. Our toll-free line is 1-855-667-8287. That's 1-855-NO-STATS. You can also email questions to methods.colloquium@gmail.com. We won't be taking questions until the end of the talk, so you might want to hold the especially the phone call. You can email anytime, but you might want to hold the phone calls until close to the end. There's also going to be a copy of the slideshow that goes along with this presentation at the link. There's a chat box in the side of your screen there, and someone's going to post a link to the slides if you want to download them and follow along. There they are. And that's it. So without further ado, Susie, welcome to the talk, and thank you very much for participating today.
Thank you for inviting me, Justin, and thanks to everyone for tuning in, if that's the right verb for this thing. I am going to present work today that's joint work with Luke Keel, my colleague here at Penn State, and Clay Webb, who is finishing his dissertation at Texas A&M and is headed off to Kansas in the fall. The paper is Treating Time with All Due Seriousness, and it's in part a response to a paper by Matt Lebo and Taylor Grant called Error Correction Methods with Political Time Series that criticizes some earlier work and some applied work using the generalized error correction model. But the points that I'm going to make, I think, are quite general and rise often in applied time series analysis and are sometimes ignored, and sometimes there's confusion over those. So there are three things that I hope that you can take away from the talk today. And the first is kind of a reiteration and clarification of our 2008 AJPS piece. And that's that the generalized error correction model is appropriate when data are individually stationary and also when they're jointly stationary and co-integrated. And in particular, we're going to make the clarifying point here that these models are appropriate when equations are balanced. And I'll talk a little bit about balance. The second point we want to make is that while fractional integration is conceptually appealing as an alternative to stationary time series and integrated time series, that estimation of fractional integration parameters is highly uncertain in samples of the size we typically see in political science. And so we don't recommend it as a general strategy for approaching applied time series analysis. And the last thing I want you to take away is really a word of caution, and that is not to ask too much of the data that you have in front of you. Overfitting, we think, is a serious problem in a lot of applied work, and so we'll talk about that as well. So I'm going to assume that many of you listening have shared the goal of applied time series analysis with myself, and that is that we want to estimate relationships among variables that vary over time, and we want to be able to test hypotheses about interesting quantities. Short-run effects, things like what happens when there is a change in unemployment in the short term, how does it influence things like consumer sentiment or presidential approval or consumer spending, but also what's the long run effect of unemployment, and what is the steady state level of either, again, consumer sentiment or spending or presidential approval for a given level of unemployment, and finally how quickly or slowly does our dependent variable adjust when it's out of equilibrium to return it to its steady state. Now, textbooks are quite useful to us in our time series class in answering at least part of this problem. We spend in a time series class up to a third of the class, maybe even more, on identifying and estimating the univariate properties of our time series. And we do this, we spend so much time with this because the decisions we make are crucial for identifying an appropriate statistical model. So I'm going to review a little bit from standard time series text for a minute to get us all kicked off on the same page. That is, the first thing we learn about are stationary time series, and the fundamental feature of a stationary time series is that when it's shocked, it returns relatively quickly to its long-run mean. Written as a simple autoregressive representation here, the parameter pi on lagged y tells us how much autocorrelation there is in y, and it must be strictly less than 1 in absolute value for a series to be stationary. And of course, our textbooks tell us here that if all of our series are stationary, we can model the relationships and test hypotheses using a variety of regression techniques. On the other hand, we might have integrated time series, and the defining feature here is that if a series is integrated, it doesn't return to any long-run equilibrium value on its own. It simply accumulates the effect of past shocks. So in the autoregressive representation here, the implied coefficient on yt minus 1 is 1. And it's easy to see that if we would recursively substitute for y at t minus 1 on the right-hand side, that y at time t is just the sum of all of its past shocks. And relationships between integrated time series can be modeled in one of two ways. If they are jointly stationary, that is, if a linear combination of our variables is stationary, we can use co-integration techniques, generally some form of error correction model. Otherwise, we have to transform the data and make it stationary before we do analysis, or we risk spurious inference. The third alternative is that a time series is fractionally integrated. And the key feature of a fractionally integrated series is that when it's shocked, it takes a long time for it to return to its equilibrium value. We can write it, it's not usually seen this way, but we can write it in an autoregressive form where now the coefficients pi on the lagged y proceed back infinitely and they decay hyperbolically. If we have two fractionally integrated series that are integrated of the same order, and a linear combination of them is of a jointly lower order of fractional integration, our textbooks tell us we can use fractionally co-integrated techniques, and usually, again, a little bit more complicated form of error correction model. Otherwise, like in the integrated case, we need to make the data stationary through some kind of transformation, usually fractionally differencing the data before we do analysis if we want to avoid spurious inference. Now, the key lesson from all of this comes in sort of the second thing that our textbooks tell us, but they're not often very explicit about, and we think there's a lot of confusion about this in applied work, and that is our equations must be balanced, which is to say the temporal properties of the left side and jointly the right-hand side of our equations must be the same. This doesn't mean that all the variables on the right-hand side of the model have to be individually of the same order of integration. But if we have a combination that is jointly stationary on the right-hand side, we're okay. We need to use the Dickey-Fuller distribution on our t-tests for hypotheses about individual coefficients that are integrated, or about joint tests that don't involve a jointly don't involve a set of parameters that are jointly stationary. So that we have to take care of that, but the essential lesson here is that our equations have to be balanced before we can be confident that we have valid inferences. So I want to say a little bit more about balance. The first thing is that if we have a stable long-run relationship, and that's usually what we are hypothesizing, what we're testing about, then that implies that an equation is balanced. And the intuition is pretty simple. I'm going to use my hands here so hopefully everybody can see me, is that if we have a stationary time series, it's going to be stochastically bounded and bounce around some mean. And if we have, as the other variable in our relationship, a time series that is integrated, it's eventually going to wander off in either a positive or negative direction, and that's because it's accumulating past errors. And as time progresses, these two things are going to get further and further apart. And so it makes no sense for us to think that they are tied together in any long-run relationship. And so in that case, we need to transform our data somehow, again, to ensure that we have balance, to ensure that the left and jointly the right-hand side of the equation are of equal orders of integration. So with that background, I want to say a few things about the generalized error correction model and time series that are individually stationary. There's been a lot of applied work that has adopted the generalized error correction model since Luke and I wrote our 2008 HAPS piece. And Grant and Lebo have been highly critical of the generalized error correction model in this body of work, including our own. In particular, we think that they raise a number of very valid concerns, and I'll mention some of these a little bit later, but we think that they fundamentally misunderstand the idea of error correction involving stationary data. And so I want to begin by showing, as we did in the 2008 piece, that the generalized error correction model is a simple linear transformation of a more familiar autoregressive distributed lag model. So normally when we have stationary time series, we render our equations in levels. And the most general form that we can write our equation is the autoregressive distributed lag, where here we have y as a function of some number of lags p of its own past, and some number of lags q of some number n of independent variables. And of course, our residuals from this model must be white noise. The additional assumptions that must be made are that the sum of the coefficients on lagged y is strictly less than 0 or 1 in absolute value, and that the x are weakly exogenous for the parameters that we care about in the model. Now, I'm going to present this as a simple p, q, n equal 1 model so that we can see how we get the quantities that we might be interested in out of the ADL model. The short-run effects are the most familiar and most often talked about in applied work, and they're given by the coefficients on xt and xt minus 1, so just beta 0 and beta 1. The long-run effects are bigger than the short-run effects. As you can see, if we simply sum the short-run effects, beta 0 plus beta 1, and divide by 1 minus alpha 1. It is this virtue of having a lagged y on the right-hand side that means these effects are perpetuated into the future, and so the long-run effect is larger than the short-run effect. The long-run equilibrium in the model is given by the expected value of x and the parameters in the model, and it tells us the steady-state value of y for a given value of x. And it's often a lot of interest to us. And then finally, the error correction rate in the autoregressive distributed lag model is simply alpha 1 minus 1. Now, as we said, the generalized error correction model is just a simple reparameterization of the ADL model, and we can see this by first subtracting yt minus 1 from both sides of the equation, then adding and subtracting beta 0 xt minus 1 on the right-hand side. That leads us to the third equation, which is the generalized error correction model. And we can see by simple substitution that alpha 1 star is equal to alpha 1 minus 1, beta 0 star is equal to beta 0, and beta 1 star is beta 0 plus beta 1. So we get the same information from both the ADL and the GECM. Now, Grant and Lebo maintain that you can't use the generalized error correction model for stationary time series. And they draw this conclusion based on some simulations that they conducted where they started with two white noise time series that are unrelated to each other. And they found two things. First, they found that the error correction rate hovered around -1, and that it was almost always significant. And the concern that they raised is that people might infer long-run relationships between x and y given that strongly significant and large error correction rate when they shouldn't. So let's consider what it means to have an error correction rate of -1. If the error correction rate is -1, that implies that in the autoregressive distributed lag model, alpha 1 is equal to 0. And so the model simply reduces to a distributed lag model, given here. And we can calculate the long-run multiplier from this model. If we start with our usual formula, beta 0 plus beta 1 over 1 minus alpha 1, it simply reduces to beta 0 plus beta 1. So the short-run effect is equal to the long-run effect. It is the total effect. In the generalized error correction model, the long-run multiplier is given by beta 1 star over alpha 1 star, the negative of this quantity. And beta 1 star, as we showed before, is simply equal to beta 0 plus beta 1. And since alpha 1 star is negative 1, this reduces to the same long-run multiplier as implied by the ADL. So y is going to return to its long-run equilibrium value after one period. Now recall that the danger that Grant and Lebo said is that we might infer from this that there's a long-run relationship. But consider what happens if x is unrelated to y. Then beta 0 and beta 1 are both equal to 0, so beta 1 star is equal to 0. And there exists no long-run relationship in the data, even with significant error correction. What that significant error correction tells us in this case is that yt is not dynamic. There is no autocorrelation in y. And so the -1 coefficient that they found is not surprising given that their simulations work with white noise series. But we don't think that this is a typical case in applied work. Most of the time our time series have some sort of dependence. And so we wanted to analyze the properties of the error correction model in some more general cases. And so we began, as did Grant and Lebo, with unrelated time series. But we specified both x and y to be autocorrelated. And in particular, we specified a range of values of autocorrelation for x. So we set rho from 0 up to 0.9 by increments of 0.1. And we chose a mildly autoregressive value of 0.5 for the YT process. And then, just as Grant and Lebo, we estimated this generalized error correction model. And when the series are unrelated like this, the true parameters of the generalized error correction model are alpha 1 star is -0.5. You remember it's equivalent to alpha 1 minus 1, and alpha 1 here is 0.5. And both beta 0 star and beta 1 star are 0, so that the long-run multiplier is also 0. So we conducted these simulations for a number of sample sizes, as small as 25 and 50, and as large as 500 and 1,000. And in the table here, I'm reporting rejection rates on the null hypotheses on various coefficients, and each row in the table represents a different degree of autocorrelation in x. And what we can see here in the column for alpha 1 star is that we always reject the false null that the error correction coefficient is 0. So we have a lot of power here. But on the other hand, the column for beta 1 star gives the rejection rates on the true null that the short-run effects are equal to 0. And the last column gives the rejection rate on the true null that the long-run multiplier is 0. And we see that these hover pretty close to the nominal 5% level. Now we also report bias on these the estimated coefficients, and here I've got all the parameters in the model. But I want to key in on the last two columns again, where the true value of these coefficients is 0. There is no short-run effect and there is no long-run effect in this model. And we can see that these the average bias in these things is very tiny. So there's no evidence that the analyst would conclude that there's a long-run relationship in the data when x and y are both autoregressive and stationary. But what happens if x and y are causally related? And this is the case that Grant and Lebo did not look at. So we simulated x in the exact same way as in the first set of experiments. But now we are simulating y as an autoregressive distributed lag model. And again, we're estimating the generalized error correction model. So if we follow the algebraic transformation from up above, then the true parameters in the generalized error correction model this time are again -0.5 for the error correction rate, but now beta 0 star is 0.25 and beta 1 star is 0.75, so that the long run multiplier in this setup is 1.5. So again, we looked at a variety of sample sizes and a variety of degrees of autocorrelation in X. And this time I'm reporting the bias first, and you can see that all of these numbers are quite small. And in particular, the bias on the effects of xt minus 1 across all the experiments that we did for all sample sizes averaged about 0.012, which is 1.5% of the true value. So it's very small. And it's even smaller on the long run multiplier, where it averaged about 1% of the true value. And there's a lot of power in the tests in this setup as well. We see we always reject the false null that the error correction rate is 0, and nearly so, always so for beta 0 star and beta 1 star. And the long run multiplier, we reject the false null about 95% of the time. So our conclusion for this is that we can use the GECM if we have data that are all individually stationary. And we can also use the GECM for data that are co-integrated. But a word of caution here is in order, and a caveat that was not made clear in our earlier work. And that is that the GECM and also the ADL and any other standard model and levels is going to be inappropriate if the data are imbalanced. And in fact, many of the simulations that Grant and Lebo did in their paper involved imbalanced equations. So they did a set of experiments in which the dependent variable was stationary, but the right-hand side variables were either integrated or explosive. Or the flip side case of that, when we had either an integrated or explosive dependent variable and a stationary independent variable. But as we said before, the long-run relationships simply don't make sense in this case. So we need to go back to the very first part of our time series course in lesson 1 and look at the time series properties of the individual series before we proceed with any kind of estimation. So there are some useful diagnostics to come out of an error correction model when we estimate it. So it's important to understand the logic of error correction. When x and y are out of equilibrium, in this setup, y has to adjust to return the series to equilibrium. So if we call the equilibrium error mu t, if it's positive at time t minus 1, this implies that the value of y is too high. It's above its equilibrium value. So it needs to adjust downward at time t. And the flip is true if the equilibrium error is negative, then yt must adjust upward because it's too low for its implied long-run equilibrium. The implication of this is that movement in y is in the opposite direction of the disequilibrium. So the error correction rate must be negative. And this is something that seems to be quite well appreciated. And if the error correction rate is between 0 and -1, then in the ADL it implies that the coefficient on lagged y is between 0 and 1. And this is the common case where we know there's a steady return to this long-run equilibrium. And the rate is given by the error correction coefficient. So if it's 0.7, 70% of the disequilibrium is corrected in each succeeding time period. Much less common, but also permissible, are error correction rates that are strictly between -1 and -2. And we can see this most easily if we think of the autoregressive distributed lag model, where the implied coefficient on lagged y takes on a stationary value between 0 and -1, but now we have negative autocorrelation. And this is going to produce a return to the long-run equilibrium that oscillates. So yt overshoots in each successive period its equilibrium value, but it does so by smaller and smaller amounts until it eventually returns to its equilibrium. But if we have error correction rates that are near or outside these bounds, then we have reasons to worry about a few things, and one of them is a lack of equation balance. If the error correction rate that's estimated is positive, it implies that in the ADL setup, the coefficient on lagged y is greater than 1. It's easy to see that it's explosive in this case. And so no long-run equilibrium relationship exists. This can also come about because we have unmodeled dynamics, maybe a structural break in the data or some other omitted variable. It can happen also if we have integrated and co-integrated series and there are 2 co-integrating relationships, but we only model 1. But the one I want you to remember is that this suggests that there is no long-run equilibrium, and we either need to respecify the model or transform the data in some way so that the equation is balanced. A very similar case exists if our estimate of the error correction rate is less than -2. And probably the more interesting case to think about is when the error correction rate is right at 0. And this implies that there's no long-run equilibrium in the data. And it can occur, once again, because we have unmodeled dynamics or we have integrated data that aren't co-integrated. So these estimated error correction rates can give us some clues about the presence of balance or how to respecify our model. Okay, I'm going to spend a lot less time on the last 2 points that I want to make. The first is, what about fractional integration? And I think here, fractional integration is conceptually appealing. I've written the general Arfima PDQ model, where P gives the number of autoregressive parameters, Q gives the number of moving average parameters, and D here is the key fractional differencing parameter, which tells us how much long memory there is in the data. And that's the conceptual appeal. It allows for both short-run dynamics and long-run dynamics. But there are some potential problems with our Arfima models that have been pointed out by many people for some time. And the key one here is that tests often suggest data is fractionally integrated when it's not. But it's also the case that spurious long memory arises in tests of short memory. And most often this happens for our culprit, again, here is unmodeled dynamics like structural breaks in the data. But it can also happen if we have short memory time series that we do a linear transformation of these, that spurious fractional integration will show up. It's also the case that oftentimes when our Arfima models are fit, an ARMA model will give superior predictions. And this we might think of as an important standard for evaluating the need for our Arfima models. In other circumstances, our Arfima models offer superior predictions, but this tends to happen only when sample sizes are large, and large in the experiments that are done by economists is 1,000. And forecast time horizons are long, so we want to forecast what will happen in the distant future. Granger himself in 1999 said that our Arfima models were conceptually appealing, but they might fall into what he called an empty box. And he said in particular here that the stochastic properties implied by fractional integration don't match those of most economic time series. So, the question that we want to ask is, can we reliably estimate the degree of fractional integration? And what we do is we are interested in particular in evaluating the performance of the exact maximum likelihood. This is the default estimator in Stata and the popular Arfima package in R, and it's one that it tends to be recommended the most often by the time series analysts. Other people have looked at simulation evidence for our ability to estimate D in a variety of circumstances, none of which quite match what we did here. We simulated the Arfima process given on the slide prior for a whole variety of sample sizes, and I'm going to present a subset of these results to you. And we allowed for a range of dynamics. So we simulated Arfima processes that had no short-run dynamics, those that had an autoregressive component, those that had a moving average component, and those that had both AR and MA components. And we did simulations in which D took on the value of 0, so there's no fractional integration, and which D took on a range of other values, 0.2, 0.4, 0.45, which is close to the stationary bound at 0.5, and 0.8. And since 0.8 is greater than 0.5, the data has to be integer difference before estimation. So in the transformed data, our estimate of D here is going to be -0.2. An important thing to note about the results that I'm going to present are that we assume in all of these that the analyst knows the data generating process. That is, they know whether there are short-run dynamics and what form they take. So the estimates of uncertainty that I'm going to present are the lower bound. So here are results for 3 sample sizes. The red line here is for samples of 100, the blue for samples of 250, and the green for 1,000. And the different panels here represent different values of D, where the vertical line gives the true parameter value. And the curves then are the distribution of the estimates of D across our simulations. This particular slide shows the case where there are no short-run dynamics. And this is the best case scenario for estimation, as we'll see. It's a little bit hard to tell, but in all cases, the mean estimate of D is downwardly biased, and this is particularly true as sample sizes get smaller. And the other thing is that as sample sizes are small, there's a considerable amount of uncertainty in the estimates. For D equal to 0.2, the range of the value of the estimated D goes all the way from negative 0.2 to a little bit greater than positive 0.4. If we add in a short-run dynamic, an AR component, we see that the performance gets much worse, and particularly in the sense of our uncertainty. But all the estimators are biased downward. And now in samples of size 100 for D equal to 0.2, the range of the estimated values goes from more than negative 0.7 up to positive 0.5. So these curves are notably lower and more spread out than in the 0D0 case. Finally, we have when we have when we have a moving average parameter. And the thing that I want you to notice from this is that it's even slightly worse. Now we see a larger range of D values across all sample sizes, and the negative bias grows. So the summary from this part of the simulations is that exact MLE produces downwardly biased estimates of D in all the models. And this is especially true, of course, with smaller sample sizes. And it's worse when the data generating process contains short-run dynamics. The estimator has a particular problem distinguishing long and short-run dynamics. And you can think about this, it's very logical that if we have an autocorrelation function, what we're trying to do is parse out which part of that autocorrelation function is due to long-run dynamics and which is due to short-run dynamics for models that can be, particularly in short samples, observationally equivalent. And the last thing is that in some cases, estimates of D range across almost all the possible values that D gives us. So there's a lot of uncertainty. But the flip side of this, and I think the more important thing to note, is what happens when we don't have fractional integration. So here we have simple ARMA models. And if we have a white noise process, the first case, we can see that we still find that D is not equal to 0 in an unacceptably high proportion of cases, but not that much greater than the 5% level. And the mean estimates are close to 0, but negatively biased, as we would expect based on the earlier experiments. As soon as we move to a case where we have short-run dynamics in the data, and here we set rho equal to 0.6, we find that in a third of the cases we reject the true null that D equals 0. And in small samples, the downwardly biased average estimate is negative 0.2. The problem is about the same in moving average models, but if we have an ARMA 1.1 model, we find in a sample of size 100 that in over 2/3 of the cases we would infer fractional integration when we don't have it. So we think that fractional integration is very conceptually appealing. It includes both short-term and long-term dynamics. But in the practical case where we have a working sample of 100 or 200, there's so much uncertainty about the estimation of the univariate properties of the model that we don't recommend fractional integration or resorting to fractional co-integration in the typical case. The last point that I want to make is, again, this caution, and it's a caution about overfitting. Overfitting occurs when our model explains noise in the dependent variable rather than the conditional expectation of y that we're interested in. The rule of thumb in the statistics literature is that one should fit one parameter for each 10 observations. But importantly, this rule is subject to the caveat that it's only true when data are independent and identically distributed. And of course, time series data tend to be pretty strongly autoregressive in many cases. And so this estimate of 10 is really going to be much too small for time series applications, and probably needs to be as much as twice that. Because again, the danger is if there's not enough information in each individual observation, the model can be tuned to fit random patterns of variation in Y instead of the quantity that we actually care about. And the likelihood of finding spurious relationships then grows, and it grows as the overfitting problem increases. So back a second to Grant and Lebo's criticism of the generalized error correction model. They looked at this particular set of 5 published articles that use generalized error correction, but we would suggest that the problem isn't with the generalized error correction model so much as that it is with overfitting. So we can see that the sample sizes were pretty small in all of these cases, and the number of parameters relatively large, so that the ratio of parameters to time periods was anywhere, or time periods to parameters was anywhere from 3 to 6, not close to the recommended 10 when the data is, of course, independently and identically distributed. There's another problem that factors in with these small samples, and that is that the power of our statistical tests are quite weak, and in particular, statistical tests that help us diagnose the presence of autocorrelation in the residuals. Keel and Kelly in 2006 did some simulations to ask how long does a series need to be to reliably detect autocorrelation if we have a lagged Y in our model, and they found that we need between 250 and 500 observations before the test had much power. So not only are we in danger of overfitting in these examples, but the ability to use diagnostic tests to help us to assess the specification of the model is considerably weak. So where does this leave us? Back to treating, we need to treat time with all due seriousness. And so again, the 3 things I'd like you to take away from this is don't ask too much of small samples. And when we say small samples, that means different things in different contexts. We have to be wary of overfitting. And when we have samples of 60 and even 100, if we have very many independent variables, it's a real danger. So we would suggest that analysts simplify their models when they have fewer observations. And know that the estimates of D, if we're going to go the fractional integration route, are highly uncertain in small samples. And here small can be quite large by our typical example cases, where small can be as many as 250. And the second thing is it's essential to make sure that your equations are balanced, to devote a lot of time to the individual time series properties of the data, and make sure that equations are balanced before you estimate long-run relationships or any kind of relationships in the data. And on the plus side, we can get some clues from the estimated error correction rates that help us to understand the nature of misspecification and the potential for equation imbalance in the data. So thank you very much, and I look forward to questions.
Okay. Susie, thank you very much for that presentation. Now I'm going to open up the floor for questions. Let me actually flash up the little thing here. You can we'll take questions from the audience. You can call in to ask a question on our toll-free line, 1-855-667-8287. I should mention that's only toll-free in the United States. I don't know outside the United States whether it's toll-free or not. You can also email questions to methods.colloquium@gmail.com. And while we're waiting for some questions to come in, I have some questions that I was taking down as the presentation went on. So the first thing I want to talk about is just a very, I think it's fair to say even methodologists, most of us are not experts on time series. And one thing I was thinking about while I was looking at your paper is the distinction between an ADL process and a fractional integration process, because superficially they look kind of the same. And it's really weird, especially when they're both simultaneously operating in a time series. You've got this 1 minus L to the D, and then a series of lags on top of that. And so the question that came out of that is, to what extent does an auto-distributed lag model approximate a fractional integration process? because I'm wondering, it seems like based on the Grant and Lebo replications that you can really get into trouble trying to approximate one with the other, but they look so superficially similar that I'm kind of wondering if there's been any investigation about how much one of them can approximate the other one in practice.
I think if we're talking about individual time series and say the AR presentation that I showed at the beginning and a fractional process, they can be very similar. As I said, they're fighting over the ability to explain, the decay and the effects of shocks over time. And particularly if we have a short sample, it's pretty hard to parse out what lag of autocorrelation is indicative of short-run dynamics and which are of long-run dynamics. And so we know that we can do a pretty good job of approximating a fractional model with short-run models that include, in particular, both autoregressive and moving average parameters. Now, for multivariate models, what happens when we estimate an autoregressive distributed lag model if we have two fractionally integrated time series? I think it's going to depend on what the true models look like, and in some cases it's probably the case that you're not going to find a whole lot of difference between them. But in other cases, we're going to find bigger distinctions between them. But almost all of this work proceeds on the assumption that we know the true data generating process at the outset. And so if we know it's fractionally integrated, then we are probably better off using methods for fractionally integrated data. But we don't know that at the outset. We have to use our samples to draw these inferences. And in that case, there are multiple models that are going to approximate the way that shocks decay over time. And so the uncertainty is really pretty high there.
Well, and so following up on this, if I'm a substantive researcher and I've got some time series or maybe a panel data, there's a whole other issue of how this applies to panel data that is in the background. And I want to draw substantive inferences, right? I want to say, oh, well, if X changes, then Y is going to change in the long run by this much. Accounting for the fact that I don't really know what the DGP really is, of course, that's why I'm doing this investigation, how wrong can I be? In other words, what are the substantive boundaries on if I apply an ADL to fractionally integrated data, or conversely, if I apply some sort of fractional integration process to a model that's not really fractionally integrated? In other words, where there's not either perfect co-integration or they're both stationary. How big of a mistake am I going to make in terms of the substantive inferences I'm going to draw? Because ultimately, I'm going to end up saying something like, when X changes, then over time Y changes by this much. Yeah. It's not a problem if I'm just attributing that to short or long run dynamics. That it's kind of substantively maybe doesn't matter so much, but if I'm going to give the wrong number, or especially the wrong direction, then that's going to be very problematic.
My experience in applying an ADL or using fractional co-integration is that most of the time we don't get different inferences from these. If we don't know at the outset which is right and we try them both, we're often in the happy world where they tell us very similar kinds of things. And I like to then be in that world where I can draw interpretations more easily from the results that I get. And this is the other problem with fractional integration. We don't have any intuition about what a fractional change is. So to say D is equal to 0.3 and we fractionally difference, or what does that tell us about the effects of X on Y? Now we can use impulse response functions and trace these things out to put it into kind of words that we know and understand. But people haven't done that. They mostly refer to sign and significance on when they use fractional integration. But I think in a lot of cases the answer to the basic question about how wrong am I going to be if I go either way is that it's probably not going to make much difference in the sample sizes that we have.
So there's some examples in the Grant Lebo paper. There's a Sharknado example, right, where you correlate sharks with something, you correlate tornado currents or something, you get sort of sharks being related to things they ought not to be related to.
Mm-hmm.
And the signs and significances are very similar, and the magnitudes even of the coefficients are similar to things that logically ought to be related to the process that you're involved in. And the implication that they draw is, well, if I can get sharks to be related to something, I can get anything related to something, and so there's a problem here. I'm taking it from your talk that you're attributing that to not to mistakenly applying an ADL to an FI process, but rather to the fact there's so little data that you could fit anything to that process.
I think that's right. And they may be right, but I think the simpler place to look for the answer to the problem is that they just don't have much information in the data. When the sample size is 45 or 60 or even 100, and you've got lots of independent variables, you may very well get results that don't make a lot of sense because you're fitting random variation. So that's the first place to look for the culprit.
So now I'm gonna ask about panels, because I think most of the data I'm dealing with usually comes in the form of a panel, not in the form of a really long time series. And that also typically means that the panel, it might not be a panel of 5, T of 5, but it's probably not going to be much longer than 20. Maybe if I'm lucky, 50. Mm-hmm. Does larger N help me on this? Larger number of units, is that going to help me draw these inferences or not?
I don't think so. I do less with panel data, but I think the answer is not really, because it's not going to give you any information about dynamics. I mean, you have to assume that all those panels have the same dynamic underlying them, and presumably that's a reasonable assumption, or you wouldn't have pooled them to start with. But it's hard if we have 20 time points to take the autocorrelation function that would be generated by that data, and we might imagine if these processes are typical of a lot of political science data where there's some degree of autocorrelation, we just don't have a lot of certainty around the estimates of autocorrelation at any given lag, and so jointly fitting a model to the joint autocorrelations to be able to distinguish something that's fractional from something that's not, it's going to be, I think, nearly impossible.
Well, I'm also thinking there's this problem of, usually in panel data, you think there's probably unit heterogeneity, right? The units are different. But there's also a problem if you try to model dynamics simultaneously with unit heterogeneity, you're going to run into, I think it's called nickel bias. Nickel bias, yeah. And the solutions to that you get these very complicated GMMs that sort of, they work in theory. In practice, I've noticed I got very odd results that don't comport with anything else. I get that GMM that tells me one thing, and then 8 other models that tell me something else. They seem to be a little sensitive to the quality of the instruments, what's actually going on in the data set, and so on. And to add this complication on top of that, there comes a point where you just say, what can I learn from this data at all? At what point do I just give up and return to doing case studies or something because I just can't get anything out of multiple N?
One is, it's easy to take a depressing kind of conclusion away, particularly from the overfitting and the Arfema stuff. That is, we just don't have enough data, not enough time periods, enough observations in so many cases to be able to learn a lot about the data. And that's kind of a sad fact. When I started doing this 20 years ago, our typical time series were very short, and now they're considerably longer, and we think we're in this world where we have all of this data. But if we're putting very many independent variables on the right, and even if we aren't, we still don't have a lot of time periods to get a good read on what the underlying dynamic is underlying an individual series, let alone how they fit together.
Mm-hmm. I have one more question, and please, in the audience, feel free to send in your questions. I haven't gotten any yet, but I will interrupt myself to give your question if you send one in. So there's this question of, if you estimate an ARMA model on an Arfema process, you're restricting D to 0, right? You're basically saying, I assume D is 0.
Yes.
Your point in your simulations is, if you try to actually estimate it, you're going to get a bad estimate in all probability. Yeah. Is it better in terms of approximation of, say, dy dx, or even just y, to use to impose an assumption that might be false, or to accept a faulty estimate of, sort of as a rough approximation. So in other words, which of those scenarios would be better for me to do? Should I basically ignore the magnitude of D but estimate it anyway, just as a part of correcting for some sort of process to make a 1, or am I better off saying I'm going to probably falsely assume it's 0, but that's going to end up getting me better answers?
You know, I don't know that we have a good answer to that question. I think that, you know, whether we're estimating D or whether we're assuming short-run dynamics, what we're trying to do is account for the fact that, you know, a variable is, the value of the variable today depends on what it was yesterday in some fashion. And so the important thing is to account for that in some way. And it's probably the case that you're going to do a reasonably good job with fractional integration, but you're going to move to a more complicated world in terms of estimation and interpretation than you would if you just assume short-run dynamics. And you know, unless your goal is to forecast, you know, many periods into the future, in which case you might do better assuming a fractional process rather than short-run dynamics. But you know, I don't know that we have definitive answers to those questions, but accounting for the persistence in an individual time series in some way is essential.
I mean, that's to me what I was trying to figure out as I read your paper. Like, okay, you know, I've got this data I'm dealing with. You know, ultimately, like I said before, what I really want to say is dy dx is a number. And I want that number to be as close as possible, and I want the confidence intervals to cover that number the right proportion of the time. I don't really care about d. You know, d is like just a thing it's not a nuisance parameter, but it's not something that's primary interest. So if I can get a good dy dx saved 10 years out, setting d of 0, fine. If I can get that estimating a bad d, but accounting in some way for the process, that's also fine. You know, I'm ultimately not going to really report that. And so that's the thing I kept kind of wondering, like, you know, if I'm, you know, at a very practical level, I'm going to walk into a class in a couple of weeks and try to tell somebody about panel data or time series data. You know, what's the best practice in this situation if you're really interested in dy dx?
Well, you know, I think the answer to that is you have a paper to write, or I have a paper to write, or your students do.
We all got too many papers to write. I just want an answer. I want something. Can't it just be easy once?
I wish.
Yeah. So we don't know. That's the.
I think that's the bottom line. We don't know.
Okay. Well, that's depressing, but okay. There aren't any questions from the audience, so I'm going to infer from that your talk was extremely definitive. So thank you very much, Susie, for appearing on the IMC this week. That's all the time we have. Next week at noon Eastern on Friday, 11 Central, there will be a presentation by Chris Zorn, also of Penn State, entitled Corpus-Based Dictionaries for Sentiment Analysis of Specialized Vocabularies. You can check out our website, which I'm now flashing on our screen, www.methods-colloquium.com, for more details about that presentation, and I believe we actually have a paper already uploaded for that presentation. So thank you, Susie, for your presentation.
Thank you very much.
And thanks, everyone, and I'll see you next week.